Now, we've seen that matrices A and B correspond to functions, and the product corresponds to another function. If the functions that result from these matrices are functional inverses of each other, we say the matrices are matrix inverses of each other. So here's an example. This is an elementary row addition matrix. The function applied to a vector with entries x1, x2, x3 adds twice the first entry, x1, to the second. Therefore, the functional inverse subtracts twice the first entry from the second. So here's the functional inverse. That tells us that the inverse of the matrix A is this matrix, which is also an elementary row addition matrix, but this time subtracts twice the first entry from the second entry. If A and B are matrix inverses of each other, we say that A and B are invertible matrices. And it's not hard to show that each matrix has at most one inverse. And we refer to the inverse of a matrix A as A to the power minus 1. So you'd read this A inverse. Why do we care about invertible matrices? Here's one reason. A matrix vector equation is guaranteed to have exactly one solution if the matrix is invertible. Let's see that. Let A be an m by n matrix and define the function f by f of x equals a times x. Now, suppose A is an invertible matrix. Then f is an invertible function. That is, f is 1 to 1 and onto. Since it's onto, for any vector b in the codomain of f, there's some vector u in the domain of f such that the image of u under f is b. That is, there's at least one solution to the matrix vector equation, a times x equals b. Now, since f is 1 to 1, for any vector b in the codomain of f, there's at most one vector u in the domain that maps to b under f. That is, there's at most one solution to the matrix vector equation a times x equals b. So if A is invertible, then for every right-hand side vector b, for every vector b in the codomain of this function f, the matrix vector equation ax equals b has exactly one solution. Here's an example, the industrial espionage problem. Given the vector b, specifying the amount of each resource consumed, our goal was to figure out how much of each product the factory was producing. So we set this up as a matrix vector equation. If we solve the vector matrix equation for some right-hand side b, giving the amount of resources consumed, are we guaranteed to get the true number of products produced by the factory? Well, is there a unique solution? If there are multiple solutions, our industrial espionage will fail. We can't be certain that we found the true number of products produced. But it turns out that M transpose here is an invertible matrix, so the function is an invertible function, and there's a unique solution. For every vector b, that's the case. The sensor node problem gives us another example. Remember that we're trying to find a current draw for each of 4 hardware components. And let's say we use 3 test periods. We record the total power consumed in each of those test periods in a vector b. And for each test period, we have a vector specifying for that test period what proportion of the time each hardware component is on. Now, to find the vector giving the current draws for each component, we want to solve a matrix vector equation ax equals b, where A is a matrix whose rows are these duration vectors. Does this yield the current draw for each hardware component? It turns out in this case that this matrix is not invertible. In particular, the function that maps x to a times x is not 1 to 1. So there's no guarantee that there's only one solution to the equation. And therefore, by using solve to get a solution to this, we might not get the right solution. We might not get the solution giving the current draw for each of the hardware components. we have to add more test periods. Let's use 4 test periods instead. In this case, the matrix consisting of the corresponding duration vectors is an invertible matrix. And so there's only one solution to the matrix vector equation AX equals B. And therefore, in principle at least, we'll find the correct current draw for each of the hardware components. Another reason for considering invertible matrices is that the matrix vector equation AX equals B is somewhat easier to solve in the case when A is an invertible matrix. Later we'll learn 2 algorithms to solve such equations. But we'll also learn how to cope in the case when A is not an invertible matrix. And finally, invertible matrices play a key role in an idea called change of basis, which we'll see later. Change of basis is a very important part of linear algebra, and we'll see it being used in rendering an image with perspective or in actually synthesizing a perspective-free image from an image with perspective.
Here's a simple but useful proposition about invertible matrices. If A and B are invertible matrices and their product A times B is defined, then it too is an invertible matrix. We'll see some examples. Here are 2 matrices, A and B. Each corresponds via matrix vector multiplication to a function from R2 to R2. The matrix A corresponds to the function that adds the second entry to the first entry. This function f is clearly invertible because the function that subtracts the second entry from the first entry is its inverse. The matrix B corresponds to the function that adds the first entry to the second entry. This function is also clearly invertible. Since the functions f and g are invertible, their composition is also invertible. And by the matrix multiplication limit, their composition corresponds to the matrix product A times B, which is this matrix. So that matrix is also invertible. In the second example, the 2 matrices are slightly bigger, but like the previous 2 matrices, these are elementary row addition matrices. Multiplication of a vector by this matrix A adds 4 times the first element to the second element. And this function is clearly invertible because the function that subtracts 4 times the first element from the second element is its inverse. Now, multiplication by the matrix B adds 5 times the first element to the third element. And that function is similarly invertible. Again, by the matrix multiplication lemma, multiplication by the matrix A times B corresponds to application of the composition of the 2 functions. So the composition is also an invertible function, so the product A times B is an invertible matrix. One more example. Here are 2 matrices, A and B. Here's the matrix product. It's not an invertible matrix, so the proposition implies that at least one of A and B is not an invertible matrix, and in fact that first one, A, is non-invertible. For the proof, we just follow the same line of reasoning we used in the first 2 examples. Given the matrices A and B, let f and g be the corresponding functions, the ones defined by matrix vector multiplication. Now suppose A and B are both invertible matrices. Then the functions f and g are invertible functions. Now assuming the matrix product A times B is defined, the functions f and g can be composed. And since f and g are both invertible functions, the composition is also invertible. So by the matrix multiplication lemma, the corresponding matrix is A times B, and that's an invertible matrix.
Now here's a nice observation about matrix inverses. If a matrix A has an inverse, then the product of A with its inverse is the identity matrix. Here's the proof. Let B denote the inverse of A. As usual, we define the corresponding functions. The function f which takes x to a times x, and the function g, which takes y to b times y. By the matrix multiplication lemma, the composition f composed with g has the property that f composed with g applied to x is the same as taking the product of AB and multiplying it by x. On the other hand, because we've said that A and B are matrix inverses of each other, it must be that f composed with g is the identity function. So the product AB must be the identity matrix. What about the converse? We've said that if A has an inverse, then A times A inverse is the identity matrix. You might be tempted to conjecture that if AB is an identity matrix, then A and B are inverses of each other. But here's a counterexample. A matrix A and a matrix B, their product is an identity matrix, but in fact, the functions corresponding to A and B are not invertible. In fact, we can see here that multiplying A by this vector and multiplying A by this vector both give you the 0 vector. So the function corresponding to matrix-matrix multiplication is not even onto. The null space of A is not trivial, and we know that that implies that the function is not onto. So f is not an invertible function, so it doesn't, the matrix A doesn't even have an inverse. So just because the product of two matrices is the identity matrix doesn't mean these matrices are inverses of each other. So it's a false conjecture. However, we can show that matrices A and B are inverses of each other if and only if both the product AB and the product BA are identity matrices. Here's the proof. Suppose A and B are inverses of each other. By the lemma, A times B is an identity matrix. Applying the lemma with the roles reversed tells us that BA is also an identity matrix. On the other hand, suppose AB and BA are both identity matrices. We define the functions in the usual way. F is the function that maps y to A times y, and g is the function that maps x to b times x. Because AB is the identity matrix, by the matrix-matrix multiplication lemma, f composed with g is the identity function. Because the product BA is an identity matrix, it follows using the same lemma that g composed with f is an identity function. This proves that f and g are inverses of each other, functional inverses of each other, and therefore A and B are matrix inverses of each other. How can we tell if a matrix is invertible? Well, a matrix is invertible if the corresponding function is an invertible function. And we know that a function is invertible if it's one-to-one and onto. Now, we have a criterion for linear functions being one-to-one. And the function corresponding to matrix vector multiplication we've seen is always a linear function. So by the one-to-one lemma, the function is one-to-one if and only if the kernel is trivial, which is the same as saying the null space of the matrix is trivial. What about onto? We're not yet in a position to characterize linear functions that are onto. So we can't quite answer this question. But if we did know whether a linear function is onto, we could get a nice criterion for whether a matrix is invertible.